Okay, in this video we are going to look at some results related to traces of the adjacency matrix of a graph. So it's going to be a very short video. So by the way, the trace of a square matrix is sum of its diagonal entries. Okay, so this particular thing is very well known to high school students. Okay, the trace of a square matrix is the sum of its diagonal entries. For example, if we consider this matrix, the trace is nothing but sum of the elements on the diagonal. So for this matrix, the trace trace of this matrix is 0, whereas if you consider this matrix a trace of x squared, so this is nothing but taking this matrix and multiplying it with itself. Okay, you get this one. And here the trace of this matrix is the sum of the diagonal elements 3 plus 3, 6, 7, 11, 14, 16. And the trace of this matrix x cube, okay, it is 6 plus 6 is 12. Okay, so that's what a trace of a matrix is. So trace of a square matrix is a sum of its diagonal entries. So we have these three simple results that is related to adjacency matrix of a simple undirected graph. Okay, so the statement reads as follows: let G be a simple undirected graph with m edges and t triangles. For example, if you consider this particular graph, okay, here the number of edges, okay, so m is equal to 8 and the number of triangles is only 2. Okay, this one is a triangle and this one, okay, only 2 triangles, so 2. And the result says, okay, trace of x is equal to 0. So that is very easy to see, okay, because we are dealing with a simple undirected graph, so it doesn't have any cycle or parallel edges. Okay, so for example, if you consider this graph G, so this is the adjacency matrix of this graph G. Okay, since it doesn't have any loop, all the diagonal entries are 0. So that says the trace of this matrix is equal to 0. So that is very easy to see. Okay, so we have this result, and the second result says the trace of the squared matrix, square of the adjacency matrix is equal to 2 times the number of edges in the graph. Okay. Okay, so anyway, let's go and verify, then after that we will prove them. Okay, so let's consider this x squared. So here the trace of this graph is 16, the sum of the diagonal elements. So here the number of elements, number of edges is 8. Okay, and let's see. So here we can see that this is nothing but 2 times a, which is equal to 2 times 8, 60. Okay, so we saw this result do satisfy for this undirected simple graph. Okay, so and again we can see that trace of x cube is equal to 6 times the number of triangles in that graph. So let's see whether that is true for this graph. So here the trace of x cube is equal to 12 and the number of triangles, in this case this triangle and this triangle, is 2. Okay, and this is nothing but 2 times t, which is equal to 12. So we verified these three for this simple undirected graph. Okay, so anyway, this is straightforward. So let's go and prove this one. So it is going to be a very short proof. Okay, so we are going to prove that trace of the squared adjacency matrix is 2 times the number of edges in the graph. Okay, so from the last video we know that if we consider the ijth entry of the squared matrix, okay, it counts the number of walks of length 2 from vertex I vertex vi to vertex vj. Okay, so this is true for any two vertices in the graph. Okay, so here we can see that if you consider ij entry, okay, so let's see what that is going to be look like. So number of arcs of length 2 from a vertex to, okay, number of walks of length 2 from a vertex to itself. So it is something like xia kind of thing. Okay, and that is going to be is just the number of edges incident on that particular vertex. So if you consider okay, this vi and vj, so here we have, okay, this kind of situation for this to be a non-zero entry. Okay, so okay, arcs of length 2. So number of arcs of length 2 from a vertex to itself is something like this thing. You start from here, move to a neighboring vertex, okay, then come back. So that corresponds to this edge. Okay, similarly it do happens for every other vertices adjacent to v1. Okay, so in the first step you will move from here to here, and the next step you will come back, something like that. Okay, and that corresponds to all these edges. Okay, and that's what I said here. Number of arcs of length 2 from a vertex to itself is just the number of edges incident on that vertex, and we know that, okay, this is nothing but the degree of each vertex. Okay, so that says if you consider this quantity xii squared, okay, that is equal to the number of edges connected to a vertex vi. Okay, so xii square is equal to the number of edges connected to vertex vi. Okay, and that is nothing but, okay, but the degree of vi in our graph G. Okay, and we know that by the handshaking lemma, the first theorem in graph theory, sum of the degrees of all the vertices in the graph, okay, that is equal to 2 times the number of edges, which is nothing but 2a. Okay, and here this summation is nothing but, okay, this quantity. Okay, so we have, okay, sigma I equal to 1 to n x ii squared, okay, that is nothing but sigma I equal to 1 to n degree of each vertex vi in our graph G. Okay, from the handshaking lemma, we know that this quantity, sum of the degrees of each vertex, is 2 times the number of edges. Okay, and this summation, it is nothing but, okay, this summation is nothing but the trace of x squared, and thus, okay, we can very easily see that a trace of the square of the adjacency matrix is nothing but, okay, 2 times the number of edges in the graph. Okay, and that we saw from this example also. Okay, so we have this result, and let's go and prove this result. Okay, so we are going to prove that trace of the cube of the adjacency matrix is, okay, 6 times the number of triangles. Okay, so that's what this statement says. T is the number of triangles. Okay, so we saw that from this example. Okay, if you consider this graph, it has 2 triangles and trace of x cube is nothing but 12. That 12 is 2 times okay, sorry, it is not 2, 6 times the number of triangles. Okay, and the number of triangles is 2, so 6 times 2 is 12. Okay, so we saw that it holds for this undirected graph. So let's go and prove the statement. So here again, what we are going to do is we are going to use the xij cubed kind of thing. Okay, so in the again from the last video we saw, okay, xij, okay, this quantity xij cube, it counts the number of paths or walks. Okay, it counts the number of paths of length, okay, in this case 3. Okay, counts the number of paths of length 3 starting at vertex I. Okay, starting at vertex Vi and ending at vertex Ej. Okay, and we know that a triangle in a graph, okay, it is a path where the start and the end vertices are the same. So a triangle is a path that starts and ends at the same vertex. Okay, so that what we are going to do is we are going to look at the xith entry of this cube graph. Okay, so that says therefore this quantity xij3, okay, it counts the number of triangles that contain, okay, Vi as one of the vertices. Okay, that contains Vi as one of the vertices. Okay, for example, if you look at this this example, we can see that if you consider this 2, okay, so here it corresponds to V1. So the number of triangles that contain V1 as the number of vertices is this one. Okay, V1, V2, V5, and the other way V1, V2, V1, V5, V2. Okay, so one triangle this way and the other triangle this way. Okay, so 2, in that case, if we look at this one, okay, that corresponds to vertex 2. Okay, vertex 2. So if you look at this vertex 2, we can see that it belongs to, okay, 4 different cycles or triangles. Okay, this cycle, okay, this cycle, then this one and the other way, and that's why this 4 is here. And similarly, you can also see that if you look at V4, okay, again the same kind of thing holds. Okay, you can look at that particular thing. Okay, so it will be like this one, okay, this one, and this and backs, something like that. Okay, okay, so that's what I said here. Xij3, it counts the number of triangles that contain Vi as the number of vertices. Okay, but here we are dealing with, so here if when we consider x113, okay, x113, in that case we considered, okay, this and the other one. So we have this clockwise and counterclockwise kind of thing. And also we can see that if you consider this cycle v1, okay, v2, v5, okay, then we have a different kind of cycle like v2, v5, v1, okay, so it is like v1, v2 using this edge kind of thing. Then we could start from here, v2, v5, v1, okay, or maybe like v5, v1, v2, okay, these all three things, okay, it represents the same kind of cycle, okay, when you consider this cycle as a subgraph of this graph, okay, so that's why that 6 comes here, okay, 2 from this clockwise, counterclockwise, and 3 from this kind of listing. So there will be a factor of 6, so we need to multiply by 6 or divide by 6, okay, and that's where that 6 comes, okay. So if you sum up this thing, you get all such triangles, okay, counting this clockwise, this counterclockwise, and these 3 ordering, okay. So that means if you divide the trace by 6, you get the number of triangles, okay, and that's from where this 6 comes, okay. So let me complete this proof. So Xij3, it counts the number of triangles that contain Vi as one of the vertices, okay, and as I said, okay, each distinct triangle will be counted twice for each vertex, okay, one that clockwise and the counterclockwise, okay, and okay, these 3 sequences kind of thing, okay. So that corresponds to a factor of 2 times 3, which is equal to 6. So we can very easily see that each distinct triangle, okay, it will be counted twice, each vertex in G, okay, so once in each direction. So if you like, we can call that clockwise and counterclockwise, and counterclockwise or anti-clockwise. So that counts the that, okay, so there will be a counter or counting of 2 in that case, and similarly, okay, we could consider these cycles in, okay, in these 3 different ways. So all these 6, okay, will come here, and that's why we need to divide by 6, okay, and that's the result. So that says therefore the number of distinct triangles triangles, okay, is going to be equal to the trace of x cube divided by 6, okay, thus we have the result, okay. So that says we have number of triangles, distinct triangles is t, okay, trace of x cube divided by 6, and that says trace of x cube is equal to 6 times t, okay, and that's what we are looking for, okay, and so we proved this one. So even though, okay, it looks somewhat simple, some kind of idea we can get from these 2 results, okay. By the way, okay, interpreting the traces of x to the 4, okay, x to the 5, etc. is somewhat difficult, okay. I think there is no direct way of counting all those things, okay. Anyway, there is a branch called spectral graph theory. You can look into that for dealing with higher powers of the adjacency matrix, okay. So in this video we consider these 3 traces, okay, trace of the adjacency matrix, which is equal to 0 for a simple undirected graph, and trace of the square of the adjacency matrix is nothing but 2 times the number of edges in the graph, and the trace of x cubed, where x is the adjacency matrix, that is equal to 6 times the number of triangles. Okay, so we can use this kind of result to count the number of triangles in a graph. Okay, in a simple undirected graph, take the adjacency matrix, take the cube and divide by 6. Okay, you get the number of triangles. Okay, find the trace. Okay, then divide by 6, you get the number of triangles. Similarly, find x squared, find the trace, and if you divide by 2, you get the number of edges. Okay.